Okay, it's being recorded now. Perfect. All right, so looking at the poll, I'm seeing a lot of votes for question 3, 4, one for question 5, and then a couple for question 6. So I guess let's get started with a popular vote. Let's get started with question 3 and 4. Um, so question number 3, that's the question. So what do we have here? We have an infinite power tower. That's its non-technical name. So we have f of x equals x to the power x to the power x, and so on. So any ideas? How do we tackle something like this where we have like an infinite stack? Okay, we'll do a really smart substitution. I'm gonna write this function in a different way. So we have y equals, so I'm gonna, instead of f of x, I'm gonna use y. So x to the power x to the power x, blah, blah, blah. So what you'll see is that you have x here, and then like the copy of the function is the exponent itself. You can just do that really smart substitution. And then we get y equals x to the power y. And now that's just an implicit function, right? It's a function of x and y defined implicitly, so we're just going to use implicit differentiation on that. So implicit differentiation, let's start out by taking the natural log on both sides. So we get the natural log of y equals y times the natural log of x. The y comes out as a multiplicative factor because of the laws of the logarithm. And then let's take the derivative. So when we take the derivative with respect to x of the natural log of y, so on d by dx, we get 1 over y times dy by dx. And then this is a product of, so we have to use product rule on that. So we're going to do y times the derivative of the natural log of x, which is 1 over x, plus the derivative of y, which is dy by dx, multiplied by the natural log of x. I have 1 over y and 1 over x, so why don't I just multiply everything by x and y? So just multiply everything by x and y, just to get rid of these fractions. So on the left-hand side, I get x times dy by dx. This should equal y squared plus dy by dx times x, y, natural log of x. And then the last step is to just solve for dy by dx. So if you just do some algebra, some rearrangement, you get dy by dx equals y squared over x minus y, x minus x times y times the natural log of x. And then if you want, you can resubstitute that definition of y back in. So x to the power x to the power x, blah, 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 all squared, x minus x, x to the power, blah, 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 times the natural log of x. Okay, so that's the derivative of this function. Another like follow-up question would be, is that for what values of x does this function actually converge? Like, for example, if I plug in a value of 1, I have 1 to the power 1 to the power 1. Okay, that's probably going to converge to 1. But if I plug in a value, let's say x equals 2, I have 2 to the power 2 to the power 2, and so on. That's probably going to go off to infinity. So figuring out what values of x converge and give me a finite value of y is actually a pretty good problem. You might think it's absolute value of x less than 1, but actually the values of x that converge are e to the negative e less than equal to x less than equal to e to the power 1 over e. So these are the values for which the function is actually convergent. Um, a related derivative to this that's pretty aesthetically pleasing. So something similar is, what's the derivative of f of x equals e to the 1, 2, 3, 4, 5, 6 x? So what's the derivative of this function? So I like calling the first derivative of this function the mountain, and then the second derivative is a mountain range. And the reason for that is, so when we compute the derivative f prime, well, we're going to have to use chain rule on this expression, right? So what's the chain rule? We have all of this. So what's the derivative of the first expression? It's just the first expression multiplied by its exponent, because this is the exponential function, e to the e 3, 4, 5, 6. And then we have to multiply it by its exponent and the derivative of that exponent. So we get 1, 2, 3, 4, 5. And then, well, we have to use chain rule on this one as well then. So it's 1, 2, 3, 4. And you can imagine the pattern is going to keep going. And now, so that's a pretty cool looking derivative. And you can imagine what happens if we take the derivative once more. So we'd have chain rule where we would take the derivative of this expression and multiply it by this, which would be like a mountain stacked with another mountain. So you just get some like pretty cool second derivative shapes with like a bunch of additions in the middle. It looks pretty cool. You guys can try it out yourself. It's way too long to write out right now. Okay, so that was question 3. Let's take a look at question number 4 now. And once you know the trick for question 3, just defining it as an implicit function, question 4 should be pretty simple. We just have f of x equals the square root of x plus the square root of x plus blah, blah, blah. And if you notice, the copy of the function is within itself. So you have y equals the square root of x plus y. You can square both sides. Y squared equals x plus y. And then just do your implicit differentiation. I'll leave that to you guys. And at the end, you should just get dy by dx equals 1 over 2y minus 1. And then you can plug in your value of y back in. So 1 over 2 square root of x plus square root of x plus blah, blah, blah minus 1. So that's number 4. That's pretty easy once you know how to do it. Okay, so the next one, do we need to state derivative theorems? Not really. Unless asked, yeah. It'd be way too long to have to state like every single derivative theorem you're using. Okay, so the next one we're gonna do is question number 6. Okay, question 6. Find the radius of the largest circle inscribed within the functions f of x equals plus minus e to the minus x squared. All right, let me get a new page. So let's just draw a picture to kind of see what's going on here. So e to the minus x squared is the bell curve function. So we have something like that, and then we have a bell curve on the bottom here because it's plus minus. And the question is asking, what is the biggest circle we can put inside here? What's the radius of this circle? Okay. Any ideas on how we're gonna approach this problem? Minimize the distance between the curve and the origin, get the tangent. Yeah, both of those are like basically the same approaches. They should give you the same answer. I'm gonna use the minimization approach. So let's say we define a point A, and point A has coordinates x, and its y coordinate is going to be e to the minus x squared. And now what we're trying to do is we're trying to minimize the distance OA, so from the origin to A. And this distance, you can just use the distance formula. It's equal to x squared plus e minus x squared, all squared. Expand that out, you get x squared plus e minus 2x squared. And OA is basically the radius of our circle. So this is r. So this is a function that relates the radius of the circle to to the x coordinate of this point A. So what we're trying to do is we're trying to find our x. We're trying to find an x star such that our x is minimized. And since we're trying to find the minimum of a function, what we can do is that what we know is that the first derivative of r at the point x star has to equal 0. So let's try finding the derivative of this function. Okay, I have that here. So we have dr by dx equals half times x squared plus e minus 2x squared to the power negative half. And then we have to multiply by the derivative of whatever this expression is on the inside. So you get 2x minus 4x e minus 2x squared. And then we can write this out a bit more neatly. So 2x minus 4x e minus 2x squared, 2 square root x squared plus e minus 2x squared. So now what we want to do is we want to equate this derivative to 0. And if you want the fraction to be 0, you can just make sure that the numerator goes to 0. So that's what we're going to do. So you get 2x, where was I? Yeah. So you're going to get 2x minus 4x e to the minus 2x squared equals 0. And then we can factor out a 2x. So 2x, 1 minus 2e minus 2x squared equals to 0. And that gives us two possibilities. Either 2x is equal to 0, or 1 minus 2e minus 2x squared is equal to 0. And then both of these, you can solve for x. In the first one, you just get x equals 0. In the second one, you get x equals the square root of the natural log of 2 over 2. You just solve for x from this expression. So now we have to check which one of these actually gives us the value for the minimum radius. So if I'll make a small table here. Here's x, here's r, 0, square root of the natural log of 2 over 2. So if I plug in x equals 0 into my function relating r and x, I get a radius value of 1. If I plug in the square root of natural log of 2 over 2 for x, I get a radius value of 0.9201. So that means that this is going to be the x value that yields the minimum radius. And maybe I can draw like a small drawing of how that's going to look. So we have this. It's going to be our function. And then that's our circle. And basically what we found is this x coordinate. So this x coordinate is the square root of natural log of 2 over 2. And then you can just plug that in back into the distance formula we had relating r and x to get the radius of the circle. So that's how you do question 6. One of the students said that you can equate the here. So this value maps to this value maps to this. One of the students said you can equate the tangents. Yeah, I think that would work as well, because at those points where the circle is just touching the curve, like the curves are tangent to each other, so their derivative should be the same. So you would have the equation of the circle. The circle equation would be Oh, y squared plus, yeah. And for r, you would plug in that value, that function of x. How can we generalize this if we have symmetry around the origin? If we didn't have symmetry around origin, if you didn't have symmetry around the origin, I would be inclined to break up the function into the different pieces and then figure out each one of those subsections and then just see which one's the minimum out of that. That's probably the best way to do that. Okay, so that's Q6. We had one vote for Q5. Q5 is a pretty interesting problem. It's from the problem plus section of the textbook. Yeah, this is basically we're going to solve this using a proof by induction. Okay, so what is a proof by induction? You should plug in 0.92 squared probably, not 0.92, because it's x squared plus y squared equals r squared, not r. So what is a proof by induction? So the way that a proof by induction works is like, let's say for example, you have a statement that you're trying to prove. Like here, we're trying to prove that the nth derivative of this function is equal to like blah, 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 whatever here. So what we'll do is first we'll solve for a base case. Like for example, for n equals 1. We're going to prove that the n equals 1 case is true. So that's the first step. The second step is assuming n equals k is true, show n equals k plus 1 is true. So now what do both of these statements together imply? Well, if I prove that the base case, which is n equals 1, is true, and then if n equals k is true, n equals k plus 1 is true. So if I plug in like n equals 1 here, so I've shown that n equals 1 is true. Then using n equals 1, I've shown that n equals 2 is true. But then because n equals 2 is true, n equals 3 must be true as well, and then so on. So by proving both of these statements, you can show that the original statement is true for all values greater than or equal to 1. So now let's actually get started with the base case. For us, the base case is going to be n equals 1. So if I plug in n equals 1 into that formula, I get d by dx equals sine to the power 4x plus cosine to the power 4x equals 4 to the power 1 minus 1 cosine 4x plus 1 times pi over 2. And I'm not sure about this yet. So 4 to the power 1 minus 1 is just 4 to the 0, which is 1. And then I get cosine 4x plus pi over 2. All right, let's try differentiating the left-hand side here. So when I take the derivative of this, I get 4 sine cubed of x multiplied by the derivative of sine, which is cosine. And then I have 4 times cosine cubed of x. And then the derivative of cosine is minus sine. And then what I'm going to do is I'm going to factor out a sine squared and a cosine squared. So what's left is 4 sine x cosine x multiplied by sine squared x minus cosine squared x. And now there's a bunch of trig identities just hiding over here, right? So the first one is the expression inside the brackets. This statement over here is just negative of cosine 2x. And then if I break this 4 up into 2 times sine x, cosine x, negative cosine 2x, then 2 sine x cosine x is just sine of 2x. So 2 sine of 2x times negative cosine of 2x. And then this expression, I have 2 sine 2x cosine 2x. So I'll bring the negative sign, and then that's just another double angle identity for sine. So that gives me negative 4 sine 4x. And now since sine is an odd function, negative sine 4x is just equal to sine of negative 4x. And then we're going to use another trig identity, which is cosine pi over 2 minus x equals sine x. And once I plug this minus 4x into here, what I get is cosine pi over 2 minus 4x, which is equal to cosine 4x plus pi over 2, which is the same thing as what we have over here. So this statement is true for n equals 1, and we've proved the base case situation. Now we have to do the actual induction step. So that means we're going to assume n equals k is true, and then we have to prove case n equals k plus 1. So we have, I'm going to write the derivative expression for the value k plus 1. So dk plus 1 dx k plus 1 of sine 4x plus cosine 4x, that's equal to d by dx of dk dxk sine 4x plus cosine 4x. And now since we assume that the case for n equals k is true, I can substitute our the right hand side of the proving statement into here for n equals k. So yeah, I get d by dx 4 to the k minus 1 cosine 4x plus k pi over 2. This 4 to the k minus 1 doesn't depend on x, so I can pull it out of the derivative expressions. 4 k minus 1 d by dx cosine 4x plus k pi over 2. And then let's take the derivative of this expression. So I have that 4k minus 1. And then the derivative of cosine 4x should give me 4 times minus sine 4x plus k pi over 2. Now this 4 to the k minus 1 times 4 just gives me 4 to the k. Then I'm going to bring the negative sign into the sine expression because it's an odd function and we can do that. So we have sine of negative 4x plus k pi over 2. And then I'm going to use that same identity we had. So cosine pi over 2 minus x equals sine x. I'm going to use that identity over here. So that's going to give me 4 to the k cosine pi over 2 minus 4x plus k pi over 2. The minus and minus signs are going to cancel out. So I have 4 to the k cosine pi over 2 plus 4x plus k pi over 2. And then we can combine the pi over 2 terms. We have 4 to the k cosine 4x plus k plus 1 pi over 2. And that's basically the expression for the k plus 1th term if we plug k plus 1 into our like proof statement over here. So we've proved the case that if n equals k is true, then n equals k plus 1 is true. So basically that's the entire proof then. Do you have any questions about this proof? I know I remember the first time I saw a proof by induction was super confusing.
What was the initial problem statement sine to the power of 4x plus cos to the power of 4x? And then we were supposed to kind of use proof by induction. I think I missed like the first, if you go back to the first page.
Yeah. The actual statement we're trying to prove is right here at the bottom of the screen.
Okay, yeah, got it.
Yeah. Where did the negative 1 go in 4 to the power k minus 1? It's over here. Oh yeah, and it got multiplied by this 4 over here. So it became 4 to the k. Okay, so we've done question number 3, 4, 5, 6. Let's do question number 1. So Q1. So Q1 says that we have this expression x to the power 46 plus x to the power 45 plus 2 divided by 1 plus x. And the question wants, what is the value of the 46th derivative of f when you plug in x equals 3? Right. So any ideas on what we should do here? Find patterns. Okay. What do you mean by find patterns? Long division? Yeah, sure, we can do long division. Find the expression that you can generalize. Oh, yeah, okay. So the dumb way to do this would be to apply the quotient rule for differentiation 46 times. So don't do that because you'll be sitting here for days and the expression is just going to get bigger and bigger. Instead, we're going to just factor out x to the power 45 in the numerator. So you have x to the power 45, 1 plus x plus 2 divided by 1 plus x, and break that into two fractions. So we have x to the power 45, 1 plus x, divided by 1 plus x, plus 2 over 1 plus x. Now if you notice this 1 plus x and that 1 plus x can just cancel out. So I get x to the power 45 plus 2 over 1 plus x. Okay. That brings us to an expression that looks slightly less nastier looking. So now, let me ask you a question. What do I get when I take 46 derivatives of x to the power 45? Yeah, exactly. You get 0. Like, for example, think of a smaller case. What happens when I take 3 derivatives of x squared? So x squared becomes 2x, becomes 2, becomes 0. So if I have x to the power k and I take k plus 1 derivatives of that, I'm just going to get 0. What I'm going to do is I'm going to break this up into two functions. Let's say that f of x is equal to x to the power 45, so that's their g of x, and then this can be our h of x. So because the derivative operator is linear, the 46th derivative of f is the 46th derivative of g plus the 46th derivative of h. And we just said that the 46th derivative of g is just going to be 0 because it's x to the power 45. Now let's try to see if we can find derivatives of this function h of x. Okay? So what do I have? I have h of x equals 2 over 1 plus x. I'm going to write that down as 2 times 1 plus x to the power negative 1. Okay, let me take the first derivative. So I have 2 times negative 1 times 1 plus x to the power negative 2. Let's take derivative again. I have 2 times negative 1 times negative 2, 1 plus x to the power negative 3. One more time, just see the pattern. 2, negative 1, negative 2, negative 3, 1 plus x power negative 4. By now, you guys probably see the pattern. Say that the nth derivative of this is, okay, yeah. So this 2 isn't going anywhere, so our nth derivative probably has a 2 in there. And then here we have a factorial expression, except like the sign of the factorial is flipping with every derivative. Yeah. So the way we're gonna achieve this is we're gonna have negative 1 to the power n times n factorial. And then so the negative 1 to the power n flips signs as n changes. And then you have that that n factorial here because the magnitude of this term is n factorial. And then what is the exponent? How is the exponent of x related to how many derivatives we're taking? Well, the third derivative had minus 4. The second derivative had minus 3. So the nth derivative is going to have minus n minus 1 as an exponent. Yeah, this is not super rigorous. So I'm not going to go through the induction proof. I'm just going to give you this. Okay, so we found that pattern for h. So what happens if I want h46, the 46th derivative? What do I get? I have 2 times negative 1 to the power 46 times 46 factorial over 1 plus x to the power 47. What's negative 1 to the power 46? Is it positive or negative? It's positive. Okay, so it's 1, so I can just leave it out. Times 46 factorial divided by 1 plus x to the power 47. And then they want f of the 46 derivative evaluated at x equals 3. So that's 2 46 factorial over 1 plus 3 to the power 47. And then, so that's 2 to the power 46 factorial over 4 to the power 47. And then I can do some mental math on this. That should be 5.56 times 10 to the 29, I think, right? Yeah, I'll leave it up to you to figure out how I did that. Okay, now I could have just given you a random answer and just how would you know? Okay, let's do question number 2 because question number 2 takes a little bit of time, but it's pretty interesting. The solution
Could you
has
just
a.
the paper down a bit just so we could see the end?
Oh, you want to see the answer?
Yeah.
Is that good?
Yeah, I just mentally did the computation and confirmed it. Yeah.
All right, perfect. Thank you for checking my answer. All right, question 2. Let's do question 2. TA sus. Hey, don't throw me out of the airlock just yet. Okay, what do we have? We got f of x equals x to the n e to the x. All right, and we want the nth derivative of this expression. Okay, it looks seemingly harmless so far. Let me take the first derivative of this. What do I get? Well, I have to use product rule on that. So I'm gonna get if I differentiate e to the x, I just get e to the x times x to the n, and then the next term would be e to the x times the derivative of x to the n. So that's n times x to the power n minus 1. Okay. You want to know how I actually learned? Oh, I used Wolfram alpha. That's what I did. Okay. F double prime x. Let's go. F double prime x. You can see that the first expression, the first term in the first derivative is just the function itself. So when I take the derivative again, I get the same thing. So e to the x, x to the n, plus e to the x, n, x to the n minus 1. And then I have to differentiate the second term. I'm going to do that in red just because it's easier to see. When I differentiate the second term, I get e to the x, n, x to the n minus 1, plus e to the x, n, n minus 1, x to the n minus 2. Right? Yeah, okay. And then I'm going to do one more derivative. So derivative of first expression, get the same thing, x to the n plus e to the x, n, x to the n minus 1. And then when I differentiate the second expression, this term here, I get e to the x, n, x, n minus 1 plus e, x, n, n minus 1, x to the n minus 2. And then I'm going to differentiate the third expression, which is basically the same as the second one. So I get the same thing, x, n minus 1, e, x, n, n minus 1, x to the n minus 2. And then I'm going to differentiate the last one. It's going to be e to the x n n minus 1 x to the n minus 2 plus e to the x n n minus 1 n minus 2 x to the n minus 3. Okay, let's see. I'm going to just circle all the like terms together. So that's the one. We have just this one here. Then we have 2 and 1. And we have 1, 3, 3, 1. So now let's look at the coefficients of these expressions, okay? So if I'm looking at the, where do I write this? I'll write this here. If I'm looking at the 0th derivative, the coefficient is just 1. If I'm looking at the first derivative, the coefficients are 1, 1. If I'm looking at the second derivative, it's 1. And then when I add these two together, I get 2, and then 1 again. So I get 1, 2, 1. And then the next one is 1, 3, 3, 1. So 1, 3, 3, 1. Yeah, so we have some binomial expansion going on. We got some Pascal triangle going. So if you see the pattern from this triangle, I can write down what the next row is going to be. It's just going to be 1. And then if I want this term here, I just add the two terms above it. So 1 plus 3 gives me 4. 3 plus 3 gives me 6. 3 plus 1 gives me 4. And then I have that 1 again. So that's going to be the next derivative and so on. So binomial expansion, another way to look at binomial expansion is like, how many ways can I choose B things out of a set of A things? So I'm just going to label some of these values. So 0, choose 0. This value is going to be 3, choose 2. This value is 4, choose 3. 3, choose 0. Okay, so let me talk a bit about this value. So 3, choose 2. What does that mean? That means I have three, let's say 3 letters, and I have to pick 2 letters out of that. So how many combinations do I have of A, B, C of 2 letters? I have A, B, I have B, C, and I have A, C. So that's 3. So the formula for A choose B, so how to choose B, how many combinations of B things can I make from A, is A factorial divided by B factorial times A minus B factorial. Okay, now since I have this and I know how the coefficients of these derivatives play out, I can write the kth derivative of this expression using, oh my god, that's a terrible sigma. No. Using the big sigma notation. X equals, okay, that's slightly better. So we're going to go from I equals 0 to k. The coefficient is going to be k choose I. And then we have e to the x in every expression. So e to the x. The power of x is decreasing. So x to the n minus I. And then do you see how we have like it goes from there's no n here, then we have n, then we have n times n minus 1, and then we have n times n minus 1 times n minus 2. So it's kind of like a factorial, but like backwards. So the way we can achieve that is by having n factorial divided by n minus I factorial. So when you expand out n factorial, you eventually reach n minus I minus 1, blah, 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 blah. And then the bottom terms are just going to cancel out that entire, like that rest of the section. So like, for example, n factorial divided by n minus 2 factorial. You can write this out as n minus 1, n minus 2 factorial divided by n minus 2 factorial. And then the n minus 2 and the n minus 2 factorial are going to cancel out. Okay, so now we have the kth derivative of this expression. Let me just plug in n here. So f, the nth derivative of this is going to be the summation from I equals 0 to n of n choose I, e to the x times x to the n minus I, n factorial divided by n minus I factorial. So that is the nth derivative of this expression. Yeah. Now we have to find out what is this n derivative when it's evaluated at a value of x equals 0. So the way I'm going to do that is I'm actually going to write down the n minus 1th derivative. Then I'm going to take the derivative of that and then plug in x equals 0. Just because that's like easier to visualize. Plus, I'll teach you something about breaking up a sigma notation. So that's from I equals 0 to n minus 1 of n minus 1 I e to the x, x to the n minus I, n factorial over n minus I factorial. So I'm going to break this sigma notation up into two terms. I'm just going to take the last term out of the sigma notation. So I equals 0 to n minus 2. And I have n minus 1 I e to the x, x to the n minus I, n factorial over n minus I factorial, plus, what is the last term of the sigma notation? It's n minus 1, e to the x, x to the n minus n minus 1, n factorial divided by n minus n minus 1 factorial. Okay.
Should the thing be n minus 2i, right where you're in the summation of n minus 2?
This should be n minus 2?
Should it be? Or
No, it should not be, because we're still choosing from n minus 1 things here.
oh, okay, yeah, that makes sense.
Yeah. So what do you notice about this expression? Well, if I plug in like the lowest power of x in this big sigma notation is x squared, and you get that when you plug in n minus 2 into this big sigma notation. So this is some function that's at least on the order of x squared. Every expression in here at least has an x squared inside it. plus we have this. So if I have n minus 1 things and I have to choose n minus 1 out of them, there's only one way to do it. So that's 1. And I have e to the x. What's x to the n minus 1? Well, that's just x. And I have n factorial divided by n minus n, that's 1 factorial, which is just 1. So you can just get rid of these two things. So the n minus 1th derivative is some function of x squared plus e to the x times n factorial. Oh, I can't show this. Okay, I'm gonna write this here. You guys can see the last line though, right? Yeah. So what I just wrote at the bottom was f of n minus 1 of x equals some function of x squared and on the order of x squared plus e to the x n factorial. And then all you have to do is just differentiate this expression.
So
when I differentiate,
is that a 0 or like big O notation or something?
Yeah, that's like big O notation.
Okay.
Yeah. So what happens when I take the derivative of something that's on the order of x squared? I get something that's at least on the order x, plus I can use product rule on this term. So when I use product rule on this term, what do I get? I get e to the x n factorial plus e to the x n factorial. Now every term inside this order of x notation has at least an x. So when I plug in x equals 0, all of those terms go to 0. So that just gives me 0. Then e to the x times n factorial. I have an x here, so when I plug in 0, I get 0. And the last term is e to the 0 times n factorial. E to the 0 is just 1, so times n factorial gives me n factorial. So that is the nth derivative of this function evaluated at x equals 0. That would be n factorial. Yes, very cool indeed.
Could you explain how it the big O notation goes to 0 when you put in?
Okay, so every single term inside this expression has at least an x being multiplied to it.
Yeah.
So if I plug in x equals 0, that means every single term at least has 1 0 being multiplied to it.
Okay, that makes sense. Everything gets 0 then.
Yeah, everything gets 0. Now the question might come up: why didn't I just plug in 0 for x in this expression? Well, I want you to do that, and then you can take out the last. So if you take out the last item from the sigma notation, similar to what I did here, and you try to plug in x equals 0, you'll get something that is 0 to the power 0. So to solve that, you're gonna have to use a limit to kind of, yeah, it's nastier, it's less fun. So I did this way instead. I highly suggest you guys focus on problems similar to question 6, where it's like you're trying to maximize some parameter of a function. Like for example, you're trying, let's say, I remember last year there was a question that like it was some function, and then you had to like figure out what is the largest triangle that can fit the triangle with the largest area that can fit under this function, something like that. And you would require like expressing the triangle as a point you've chosen on the function, and then trying to minimize the derivative of the area to the value of x. So try to look through your textbook to find questions like this to practice. Another question I kind of remember was something regarding related rates of change. So it was like you had, what did you have? You had a boy running, and then you can imagine There's a balloon here with like a candle on top of it, and the balloon was rising, and the person's running, the balloon's rising, and the question was asking, how does the shadow of the person, what is the rate of change of the shadow of the person with time? So you have like some similar triangles going on here. So there's similar triangles going on here. The person's running, so this vertical line is kind of moving in this direction, while this line is floating up. So this is becoming bigger and bigger. So kind of figuring out like how that shadow is changing in size with respect to time was, I think, one of the questions last year. And other than that, just make sure you're good at doing derivatives. I believe that was a midterm question. No shadow because air blows again. Yeah, do we have any other questions for today, or we good?
Do you know how much the delta epsilon stuff is going to be emphasized in the midterms? Like, I'm
You
sure
will
it's
have
probably it's going
you
to
will
be
have
there, right?
at least one question, in my opinion, and at least one sub question somewhere else. And by like one question, I mean like a 10-point question or something.
So it's going to be pretty difficult.
Yes. You got this, though. You got this. Come on, you guys are NSI.
Is there solutions for like the quiz stuff for the previous quiz questions?
You can ask your friends that got full marks.
Okay.
If you have friends that have full marks.
Yeah, I'll ask her on the Discord. Yeah.
Yeah, and like if you guys have like any questions regarding the quiz and like you guys can't find the right solution, just like email me and then I can help you. I know someone emailed me in the morning. I still have to get back to them.
Yeah, got it. So if you have friends.
This chat's killing me. All right, see you guys.
All right, see you guys.